All right. Lecture 6. Is that right? Somehow that feels wrong.
I think it's because we started counting it on Wednesday week 1.
Yeah. Okay. Yeah. Perfect. We'll figure that out. All right. So lecture 6, quantum random walker. So for this lecture, we're going to do a specific spin system, and it's a spin system that we already introduced in the previous lecture. This is a recap of the previous lecture so let me just finish. It's going to be a spin system, which I call a random walker, and we're going to look at the probability function for this random walker, and we're going to get the probability function written down explicitly. And I'm going to compare it with a classical random walker. And part of the theme and the idea of looking at these two systems is try to figure out the differences between the classical and the quantum. So let's go where we finished last lecture. It was our spin system where we had the Hilbert space made up of copies of C2, and each copy of C2 represents the configuration of a spin up or down. And I write configurations by denoting the location of the upspin. So in here, this is going to have L positions for your spins. And in here, I write, and in the L positions, the spins could be up or down, but it's enough to denote the places where you have upspins. And you can have from 0 to L upspins. And the specific system that I introduced in the previous lecture was the XXZ model. It's also called Heisenberg-Ising spin 1/2 chain. And this model is on a ring, and it's made up of local interactions of neighboring particles. And the specific interactions, you can write them explicitly using the spin operators that we introduced in the previous lecture. The superscript indicates that it's acting on the J copy of the tensor product, and this one on the J plus 1. So this is going to be acting on neighboring particles. And so this is the spin operator in the X direction, the spin operator in the Y direction, and the spin operator in the Z direction. So these are going to be the local interactions. You can actually write it and see how the local interactions act on basis elements. So in here for the J and J plus 1 locations, if two particles are next to each other, it doesn't want to change if two upspins. Oftentimes I think of upspins as particles and downspins as holes. So maybe you'll catch me changing the wording, but when I say particle, I mean upspin. So nothing tends to happen, and when there's an upspin and downspin, then it's trying to flip to a different configuration. It's trying to switch the flips, and also in the other direction. And then when there's two downspins, two holes, nothing happens. And in here, if we write this as the local interactions in this as a matrix form, we get this matrix, and this matrix is the matrix that we actually looked for the heads-tails system, where we identified heads as up-down and tails as down-up. Am I missing one here? So the system that you guys worked on already corresponds to L equals 2 and N equals 1. And then what was the other thing that I wanted to remark? Oh, the other thing is that there's a conservation of upspins in this from this Hamiltonian, these local interactions. So in here, since nothing happens, there's nothing going on. But in this one, where you actually are changing configurations, you notice that the number of upspins in this configuration is the same as the number of upspins here and the number of upspins here. So in this dynamics, we're not introducing more upspins as time is progressing, the number of upspins remains constant. So whenever we look at our Hilbert systems, we can fix the number of upspins. It's going to stay constant. So we can just consider systems with a fixed number of upspins and treat them separately. So any questions about this? Oh, what? What is this? Jeopardy? Uh-oh, we've hit a Jeopardy question. You guys know how this is played? I give you the answer, you give me the question. Definition of an object or substance having a physical property that has a different value when measured in different directions. A simple example is wood, which is stronger along the grain than across it.
What is anisotropic?
Bingo. That is the right answer. What is anisotropy?
Technically, that's the question, right?
Yeah, that's a question, yeah. Anisotropy. For me, I kept seeing this in this like XXC literature a lot, and they were like anisotropy, and I didn't know what the vocab meant. So you'll see this sometimes. And going back to our model, can anyone spot the anisotropy parameter? You?
There's a difference between if you're measuring up and down versus down and up.
Not quite. Anyone else? So remember, anisotropy is difference in directions. Which directions do we have here? Not quite. That's not what I mean when directions. What's that? Yeah, the z direction. So we have x direction, y direction, and z direction. And the anisotropy parameter is the delta. So this is what people call an anisotropy parameter. And it's to make it Hermitian, to make the Hamiltonian Hermitian. This has to be a real number. And this is why it's called XXC, because the x and the y coordinates have the same strength of this Hamiltonian. So you can't tell them apart, this direction, so the x and y directions. And then the c direction, it's different because it has an anisotropy parameter. So just FYI. This is a terminology that took me a while to figure out, but it's not difficult. All right, so now that we had some fun, let's go back to math. So this is the example that I want to look at in specific is this example where is the XXC, L is equal to L, meaning that it's going to be any L. That's going to be a parameter that's going to be fixed, and n is equal to 1. So in this case, I'm going to have my ring, and then I'm going to have a single upspin, and the rest of the positions are going to be downspin. And I want to see how this upspin is going to evolve over time. And again, so this is going to be, if I have my upspin starting at some position, and actually, based on the notation that I have later on, I think this is the notation that I have to be consistent. And I want this, no, this is going to be, so I want the wave function. What's the probability that the wave function, that the upspin is at position x, that we measure at position x at time t, when we start the system at position x naught. X, actually this is minus x naught. All right, I think that's correct now. So for this system, the probability of measuring the upspin at position x is going to be given precisely by this formula. It's a double summation for the parameters L1, L2 from 1 to L, and then you have this whole mess. And for comparison, I have the probability function for a random walker, a classical random walker, on a circle of the same length where the random walker can jump to the right with probability 1/2, and it can jump to the left with probability 1/2. So this is going to be my comparison point. And here, this doesn't seem like much. It's hard to tell the two functions apart or what is the difference. So it helps to actually graph these things. So let me see. This is some script that I wrote. I was learning how to do 3D plots first. And so I start with the probability function. I define it there. This is for a specific initial condition. And I actually take the size of the ring to be 41, the length of the ring. And I look at time from 0 to 22. And the initial position is going to be 1. And I plot the probability function for the position of the upspin. And you see initially the position of the upspin at time 0 is localized to the position 1, and that's because that's our initial condition. And then as the time evolves, it starts spreading out. And then it starts having this kind of like it spreads out in a linear way, and inside that linear cone, there's some fluctuations in between of places where you can find it or you can't, or it has high or low probabilities of finding the upspin, measuring it. And here, I increase time to 20 to 40 seconds, or actually it's unitless, and h bar is equal to 1, so take that. So in here, we see that it keeps fluctuating, and there's some areas of high probability and areas of low probability, and this behavior is consistent with this interference behavior of quantum systems that is not present in classical systems, where you can have constructive or deconstructive interference. And this is what's going to create areas of high probability and low probability in this quantum fluctuations. And then I also wanted to figure out how this is going to look as time increases. This time is 2000 and 2040. And we see these fluctuations. We still see the fluctuations. The thing that I find interesting here is that you still somehow can capture the information of where the particle started. Because you see in the middle, there's these two yellow peaks that all of a sudden get really high at certain times. And this is some sort of signature that's left over from the initial locations. This is just qualitative, and it's speculative that you can still do it. I haven't checked it, that you can necessarily do it mathematically, recover at infinite time. But I kept looking at time 20,000 to 20,040. And this is the probability function at later time. And the fluctuations keep growing and they keep getting higher. And you just kind of get this kind of like noisiness quantum fluctuations. So this is what this first probability function is giving us, this like high fluctuations. And if you think back to the case that you worked on with L equals 2 and N equals 1, we had this cosine squared, which were fluctuations. And as time increased, the fluctuations stay the same. In this one, if you go across space, you have more fluctuations, and across time you have some other fluctuations. So it's something to think about. And then for comparison, I look at the probability function for the classical random walker on the circle. And this is what I get, something much more tame. Again, you see that near time equals 0, you have a localization of the probability near the origin, where the initial location, and then the probability starts spreading out. And here, we don't see the fluctuations anymore. And here, there's no interference behavior. All the contributions are constructive, so we don't see these fluctuations. Question? Yeah.
What is like the setup of the system? Like what are you actually, like what is the system that you have? Like before we had these like spins on the, on the ring. What is this one?
So in this one, let me draw it out. So in this one, this is gonna be a ring, and then I'm gonna have at a position X, I'm gonna have a particle, and then it's going to try to jump to the left with probability 1/2, and it's gonna try to jump to or right with probability 1/2, and left with probability 1/2. So this is in continuous time, but in the discrete time case, the idea would be that you flip a fair coin, and if it's heads, you move to a right. If it's tails, you move to a left. And you're on a ring that's of length 0 to L. And so in here, the analogy that I'm making is that an upspin corresponds to a particle, and downspins corresponds to holes. Holes. So vacant positions. So a configuration where I had something like, let's say, down, up, nope, down, down, and this is for L is equal to 4. This would correspond to a configuration where the upspin or the particle is at position 2. Yeah.
So are you like continuously doing that coin flip like over time? Okay.
Yeah, so the idea to get continuous time is that you start flipping the coin faster instead of like at each unit. The unit interval at which you flip the coin is shorter, and then you adjust the probabilities of the coin to land heads so that you're not moving too fast. And it's a limiting behavior, but the discrete case kind of has that intuition already. But this is the rough idea. Does that make sense?
Yeah.
So let's continue looking at the graphs a little bit. So in here, and this behavior is dissipation, and that's typically found in nature, and like the typical systems are heat equation where there's a dissipation of heat that just kind of spreads out, and this is kind of the type of behavior that random walkers have. They have dissipative behavior where everything spreads out, and in here I started looking at the same kind of windows of time and see how it evolves over time. You still have this hump in the middle, but now the fluctuation from the values is not that big. It goes up to 0.08. And actually, let's, for comparison, see the fluctuations in here at time really large. The fluctuations go from 0 to 0.16. So in here, even already at small times, the fluctuations are getting smaller. It's getting spread out. And then at times 2000 and up to 2040, this is actually, you still have this hump, but this is actually a little bit misleading graph, because this is actually telling you that if you look at the bar graph on the right, that the value is 2.4 times 10 to the negative 2, and then the the z-axis, it tells you the error of 2.4. So the difference at 10 to a negative 12 digits. So everything is actually already pretty flat in this case. And then at the 20,000 time, the computer can't tell the difference between the values, and it's just completely flat. So for classical random walkers, as time goes to infinity, everything gets well mixed and everything flattens out. So these are the two differences that we see from the classical and the quantum. And one other difference that you'll see, and which actually is part of the reason why these quantum random walkers are useful in terms of search algorithms and quantum computing, is the speed at which the probability function spreads out. So if you compare this one, and let's go over here. So especially at initial time, come on. So especially at early times, you try to see how the probability function spreads out. You look at this one, and you can see that this probability function kind of stays concentrated longer than the quantum one. And the quantum one spreads out much faster. And this allows you to search for things faster. So this is what gives you speed up over the classical case in terms of the quantum algorithms. And here, the speed of the spread out is linear for this quantum case, and the speed of the spread out in this classical case is proportional to square root of time. So those are the two other qualitative behaviors to take a look at. So you already see it here, and this is what's going to make a difference later on. Questions? All right, so now that we looked at graphs, the goal for the rest of the lecture is to actually derive this formula. Yes?
What is the difference between those two formulas?
So the formula up top is going to be, for the quantum case, the probability of finding the upspin at position x at time t. And the one in the bottom is the probability, this for the classical case, of finding the particle at position x at time t. So it's going to be classical versus quantum. And it turns out that deriving both formulas uses very similar ideas, and I'm going to focus on the quantum case and derive that formula. In most cases, generally, it's not easy to write down explicit formulas for the probability function, and there's a class of models where people can actually write the probability functions, and the idea is to try to analyze those problems to death to actually try to get meaningful behavior that you can extrapolate to other cases where you can't write it explicitly. So it's kind of a proof of concept or a case study that kind of informs our intuition. So this is going to be the thing that we're going to focus on for the rest of the lecture. We're going to work on deriving this formula explicitly, which you've already done it for L equals 2. And the idea is that it's going to essentially mimic what you've done already for the case L equals 2. The main difference between the L equals 2 and the general case is that in the L equals 2 case, you had a 2 by 2 matrix that you had to find the eigenvectors and take the exponential. In this case, the corresponding matrix would be an L by L matrix. So you have to find a bigger set of eigenvectors and eigenvalues and take the exponential of the matrix. So it becomes a little bit more complicated. And when you actually have L equals L and N equals N, the size of the matrix becomes L choose N. And these matrices start getting huge. And diagonalizing a big matrix is difficult. And you can make a research career just diagonalizing matrices. And that's actually what I've done. I just diagonalize these matrices. And while we're doing this computation, something to think about and try to reflect on is what is happening in these two systems. What's the difference that gives the random case some stability as time goes to infinity versus the quantum case where we don't have stability and we have fluctuations. So this is something to think about. Why are the two systems qualitatively different? And what's leading to this difference? This is just a question to think about throughout the lecture. And a hint is to think about the eigenvalues and try to figure it out that way. I think that's one way to actually grab a hold of, see why these two things are different. But this is something that I'll let you think about. So again, this solving this system, the evolution of this system essentially goes through the same basic ingredients of what you've already done. It's going to be eigenvectors, eigenvalues, diagonalization, and then solving. In this case, it's slightly, the same ingredients are there, but I put them together in a slightly different way. And in particular, when I diagonalize the matrix, I do it slightly different. But I change it to an equivalent problem. But in any case, in here, which doesn't look necessarily the same, but turns out to be the same thing. But in here, I start with finding the eigenvectors. So I have a candidate eigenvector, psi, and I write it in coordinate form, where it's a linear combination of this basis elements. X is the position of my upspin, and it could be from position 1 through L. 1 through L, and it has some coefficient. And I'm trying to find the eigenvectors of the Hermitian matrix. So really I want to say H psi is equal to E psi, and there's no X here. And this is for some eigenvalue that I call E. And if I write the action of H on psi explicitly in this format, I get that the coefficient in front of X is going to be given by this. And if I write the action of this, I get that the coefficient of X is going to be given by this. Yes?
So is H not necessarily Hermitian?
It is Hermitian.
So is the eigenvalue real?
Yeah, we already proved that. So to save face for myself, I'm going to say that the reals are inside the complex. Yeah, that's a good point. And here in quantum mechanics, E, the eigenvalue, is always going to be real, and it has the interpretation of energy. So that's something good to think about, especially since I've given you the previous hint that the difference is in the eigenvalues. So keep thinking about that. So by looking at the action of H and trying to find eigenvectors, we have that the coefficients U of X have to satisfy this identity to be an eigenvector. And in here, the first step is to guess a solution for the coefficients. And the guess, because in here, what we've done here is we established a difference equation. This is the discrete analog of a differential equation. So we're just solving a discrete differential equation. Yes?
What are the x vectors again?
In here, this is x is going to be just a number between 1 and L. And it's not for n greater than 1, it's a vector. It's a n vector. And n is equal to 1 here, so it's a 1 vector. And it's a position of the upspin.
So the cat x's, those are...
The position of the upspins. Yeah, it corresponds to the configuration. So if I put x, it corresponds to the configuration down, 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 up at position x, and then down, 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 down. So this is just shorthand to denote the location of the upspin. And this, for the different x, is going to give me all the configurations for one upspin in a ring of length L. So, and since there's only one upspin, it's just one number between 1 and L. So we've boiled down the problem to solving a discrete differential equation. And in particular, this is a linear equation. So just using what you've taught in your basic ODEs class, the idea is to just guess the solution. In the continuous case, you will guess a solution e to the lambda x, something like this, for some lambda that you'll figure out later. In this case, since it's discrete, you guess c to the x for some complex number c. And so I plug in this guess in this equation. I obtain this. And then I just divide by c to the x. And I get a formula for the eigenvalue. So the eigenvalue is going to be given by this parameter c for a guess. If the eigenvalue is equal to this number, then the previous equation is satisfied if we have u of x. We still have one more constraint, and it's periodicity. In all this notation, I've been a little bit sneaky, but I've been identifying L plus 1 with 1, since we're periodic. So what that means is that the coefficients need to satisfy this periodicity condition. And if I plug in my guess, I get that c to the L has to equal to 1. So this parameter c for the guess of our solutions have to be roots of unity. And putting this together, I have that my eigenvectors are given by this formula, where c is a root of unity, and it's a linear combination of these positions of the upspins. How many eigenvectors have I constructed here? L, yeah. So this is giving me L eigenvectors. What's the dimension of the matrix? L. How many more eigenvectors do I need to find? L minus L. 0. So these are all the eigenvectors. There's in this case, it's pretty clear that these are going to be all the eigenvectors. For higher n, it becomes a little bit more subtle that we can actually find all the eigenvectors with a similar procedure. Namely, you have to actually show that the eigenvectors are linearly independent to make sure that you found all of them. But in this case, it's kind of straightforward, or it's easier to believe. But we found the eigenvectors and we found the eigenvalues. And now we need to diagonalize. And this is where I take a different approach than what you did in the simple case in the quantum coin. In particular, I note that the action of the Hermitian matrix on an eigenvector, which I now denote by this C index. And here I have C is some e to root of unity, or rather, the action here on this eigenvector of H is just multiplication by a constant. And in this case, you can write that the solution, if you started in a multiple constant of this eigenvector, the solution is just going to be e to the it over h bar times e times this. So in this case, it becomes, since you're just working on a one-dimensional eigenvector subspace, it becomes as if you're solving a one-dimensional matrix equation, which is just taking the exponential. In that case, you can take the exponential just by taking the normal exponential, because it's just a constant. So you don't have to worry about it. So with that observation, you can actually, if you can write your initial configuration as a linear configuration of the eigenvectors for some constants C of z, then you can just solve the solution by throwing these terms in front of each of the eigenvectors. So the solution at time t is going to be given by this. And this is essentially your diagonalization problem. If you can write any initial configuration as a linear configuration of these eigenvectors, then this is going to give you your diagonalization. So this is writing the matrix problem of diagonalization into a coordinate version of the diagonalization problem. So the question is to figure out these coefficients, these constant coefficients.
What's the notation with the sum?
Yeah, good question.
O and Z?
Yeah, so in here, I'm saying that, let me see. This is going to be the summation over all C such that Z to the L is equal to 1. So this is just going to be the summation over e to pi I k over L such that k is from 1 to L.
Should capital E have a subscript Z so you know it's associated?
Mm-hmm. Yeah. So this is the energy depends on C. And this EC, we already said that it's equal to this. Yeah, thanks. Yeah, so energy depends on the eigenvector. So the diagonalization problem then becomes the problem of finding these coefficients, C sub C, such that the initial configuration is equal to the linear combination of these eigenvectors. And here I write this eigenvectors explicitly. This is the formula we have for them. And then I switch the summations. And I see that the coefficient in front of this vector x is given by this formula. And by looking at the coefficients on the left side and the right side and matching them, because this creates a basis, then the coefficients have to match. Meaning that this formula for the coefficients, this linear sum, has to be equal to 1 if x equals to x naught mod L. So if their difference is x minus, if the difference of x minus x naught is a multiple of L, then this should be equal to 1. This is because we're thinking of this as a periodic system. And if it's not, the coefficient should be 0. And this is, again, by matching the coefficients in front of the x's on the right and on the left. So this is going to be my diagonalization problem. And this is just the problem of finding the initial conditions. So the way that I find this diagonalization problem is by this following two claims. My first claim is that this indicator function of x equals x naught mod L, I can represent it and write it as a pair of contour integrals, as the difference of two contour integrals. And the second claim is that this difference of contour integrals is equal to this linear combination of that gives me the initial conditions. So it's a two-step process. And if you're not familiar with contour integrals, these are line integrals in the complex plane. And in here, the contours that I'm taking, the line integrals that I'm taking are going to be two circles. One that's bigger than 1, radius 1, and it's going to be the line integral is counterclockwise. And another one, which is of radius epsilon, that has radius that's also counterclockwise, that has radius less than 1. So these are going to be line integrals in the complex plane. And the driving force for this contour integrals in the complex plane is this residue theorem. And this is what we use. That the value of a function at a point C naught, you can write it as the contour integral. Well, I think this should go the other way. You can write it as a contour integral of f of c dc over c minus c naught, where this contour is any contour that contains the point c naught, so that the function f doesn't have a pole, or it doesn't go to infinity anywhere inside the region bounded by the curve. And in particular, due to these conditions, you can really just change the shape of the curve as long as you don't go over any region that contains a pole or a point where the function f goes to infinity. So this contour, if nowhere around here I have a point where the function f goes to infinity, then I can really just change this contour to something like this, arbitrarily small and arbitrarily close to c naught. So this is going to be the residue theorem, and it allows me to take my path and just move it around. And through this action of moving my path, I'm going to be able to show both claims. So the proof of claim 1 is I have this integral, and what I do is I do a series expansion of the denominator on both sides, and I use the residue theorem, and this is going to tell me that this function is going to be the indicator for x equals x naught plus kl. This is for k's less than or equal to minus 1, and this is going to tell me that I have the indicator function for k's greater than or equal to 0. And this is for any constant multiple of L, and this is equivalent to this indicator function. Yeah?
Can you run a couple steps so I can see what you wrote the claim? looks like there's that's in the second integral, z to the x minus x naught, and then it looks like there's an extra -1 there.
Yeah, sorry. I meant to erase this one. So this is how I prove the first claim. I just do the residue integral and I do the series expansion. And then the second claim, I'll wrap up here soon, is I take this idea that I can deform these line integrals. And the first, the starting point is this formula, which corresponds to this circles. This is my complex plane, thought about as a sphere. And we have singularities, places where it goes to infinity at 0 and at infinity. And what I do is that I take these paths and I move them in. So I have something like that's like this. And I go a little bit further and I try to touch these two curves as much as I can, but I have some singularities along the roots of unity. So the best that I can do without crossing any of the singularities is have a collection of circles centered around each of these singularities, each of these roots of unities. So this contour integrals becomes a sum of contour integrals that are centered around each of my roots of unity. And those are the roots of unity are the positions where that are solutions to my equation c to the L equals 1. And that's how I built my eigenvectors. And so in here, I actually go through doing the residue computation. And in here, computing this residue is equal to this. And I can actually split this term up and to the c and this. And then I have that my coefficients are going to be given by this formula. And each k is just indexing each of the roots of unity. So in here, I actually obtain my formula for the coefficients that are going to give me the linear expansion. So in here, I'll just wrap up. Now I have the formula, I have the coefficients, and I can write the wave function with this energy. And then to get the probability, I do the modulus square in front of the coefficients. And then I get this formula. And so that's how I obtained that formula. All right, it's time's up, but any quick questions?
Can you go back to the page where you showed the coefficients that you found here?
All right, that's class.